Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we are going to consider some applications and examples related to Lagrange equations, and towards the end we will also be looking at the concept of conservation principles arriving out of the Lagrange equation itself. So the discussion point of this module will be, as I just said, Lagrange equations and conservation principle. Okay, so the example that I have, so let us straight away dive into this example. The problem says, consider a block of mass m sliding on a smooth wedge of mass capital M and angle alpha. Which itself slides on a smooth horizontal floor. The entire motion is planar. And we have to find the Lagrange equations of motion. Lagrange equation of motion, and also we need to find the acceleration of the wedge. Let me write this statement and it will be fairly clear as to what the problem setup is. So acceleration of the wedge, and the second is the acceleration of the block. Okay, so the problem is that we have a wedge. This is a wedge which is sliding on, it's given on a smooth horizontal floor. So the floor is smooth, the floor is horizontal, and the wedge is sliding. So let us say we have this sort of axis. This is our x-axis, y-axis. So the wedge is experiencing a horizontal motion, so the velocity will be x dot. And on the wedge we have a block of mass small m. The mass of the wedge is capital M, mass of the block is small m, and the block is moving along the wedge. Let us not confuse our axis with x and y. X and y are the variables. So let me denote the axis unit vectors as I and j. So the velocity of the block is x dot. The velocity of the wedge is x dot, and the velocity of the block on the wedge is, let us say, y dot, which is along the wedge. Right now, so we need to find, had it not been the Lagrange equation, had we not approached this equation with the Lagrange setup, then the motion is very complicated. We have to write the force balance separately for the wedge as well as for the block, and also there will be a set of normal reactions which are driving both the block and the wedge, which are eventually going to cancel. So those are the constraint forces we have to account for in the equations, and in this problem we are aware that we don't know the constraint forces. So doing those problems, doing these types of problems using the equation Newton's second law, will be typically hard, or if not at least very complicated, and some of the quantities will be unknown, like the constraint forces. So the Lagrange equation comes to a rescue here. So we write down the Lagrange equation. To do that, let us write down first the kinetic energy of the system. So the kinetic energy of the system is going to be half the energy of the block, the energy of the wedge, which is half m x dot square plus half m x dot whole square plus y dot square and plus 2x dot y dot cos alpha, right? 2x dot y dot cos alpha. And where alpha, let me say that alpha is the angle that the wedge subtends, or the angle of the wedge that is given, right? So then let us say now we also have to calculate the total potential energy of the system. Now the fact is, let us say the wedge is at zero potential, or the floor is at a potential 0, the wedge is at 0 potential. There are no dimensions of the wedge given, but at least the block is on the wedge. So we will only have the potential energy of the block, which is the vertical distance. The vertical distance is going to be y cos alpha. So we will, hold on. So we will have, let me call this, so this is y dot, so this is our y, the distance traveled by the block, and y cos, we will have the potential energy as so this vertical distance is going to be y sine alpha, right? Because alpha is this angle subtended. So now the potential energy will be minus mg times the vertical distance, which is y sine alpha, and we see that now we can write down the total energy, but we don't want that. We want to find the Lagrange equation of motion. Clearly there are two generalized coordinates, x and y, right? And then, which means that for each generalized coordinates we are able to write the Lagrange equation of motion. So all we need are these quantities to write the Lagrange equation of motion, del t del x. So we see that t is not a function of x, so del t del x is 0. Here we need to be very careful, because we are now going to treat x and x dot as independent variables. We understand from the physics point of view, we understand they are not independent variable. But from mathematics point of view, we are treating it as an independent variable, right? Because we have to evaluate the Lagrange equation now. So this is something the listeners need to be very careful when they are evaluating these derivatives. So partial t partial x is 0, and partial t partial x dot is m plus m x dot plus m cos alpha y dot, right? So we have partial t partial x, and then we have partial, so this is the kinetic energy. We can see the kinetic energy only depends on x dot and y dot. So certainly there is a derivative of x dot. And then similarly we can find what is for the potential. We will not have any partial v partial x, so that is 0. Its only potential energy is only a function of y, and there are no velocity content in the potential energy. So this quantity dv dx is 0. And similarly we see that dt dy is 0, because t doesn't contain any y variable, but dt dx, dt dy dot is m cos alpha times x dot plus my dot. And we see that then dv dy is minus mg sine alpha, and of course dv dy dot is 0. So now we are ready to write down the Lagrange. Remember, we have to identify. In our previous module, we wrote down Lagrange equation for two setup. One is for standard system and one is for conservative system. Now we see that this entire setup only involves the weight of the masses. So this is clearly a case of a conservative system. So we write down the Lagrange equation for the conservative system. So here is what we have. The Lagrange equation dt of partial t partial x dot minus dt dx is equal to minus partial v partial x. So we have the Lagrange equation of motion. We plug in the quantities of t and v here, and of course the second equation that we have is with respect to y variable. Each generalized coordinate is going to give us a separate Lagrange equation. So for y now we have the following: partial t partial y dot minus partial t partial y is equal to minus partial v partial y. Now when we plug in all these values of t and v, we are going to see that this is going to be d dt of we will see that we plug in t doesn't have any x, so this is also 0, and v doesn't have x, so this is also 0. So the only quantity remaining is this d dt term. So d dt of m plus m times x dot plus m cos alpha times y dot, and we set this equal to 0. Okay, so then the next thing is we see, well, what is it? We see again we start plugging in for the y relation. The y relation will be again d dt of this whole quantity, this time with respect to y. So this will be m cos alpha times x dot, m cos alpha x dot plus m y dot, and this is equal to mg sine alpha. Right, and from this equation, from these two equations, we see that x double dot is minus mg sine alpha cos alpha by m plus m sine square alpha. We solve these two equations. So essentially the unknowns of the problem here are x dot and y dot. We have found the equation in terms of x double dot and y double dot. We can integrate it. Well, we don't want to integrate here because the question asks us to find just the acceleration. So I'm just giving you the answers here. So y double dot is m plus m times g sine alpha divided by m plus m sine square alpha, and those are my acceleration. Okay, so then what have we got here is, let us look at another example. I will go to the next page to show you the second example. The example that we have is the case of a rolling cylinder inside a hemisphere. So a solid cylinder with G and radius A rolling on the rough inside the surface of a fixed cylinder with center O. Right, so a solid cylinder with G and radius A rolling on the rough inside the surface of a fixed cylinder with center and radius given by B greater than A. We need to find the Lagrange equation of motion and deduce the period reduce the period of small oscillations. About equilibrium. Okay. So what we have is, so the problem is that we have two concentric cylinders here. One is a larger cylinder of radius B and one is a smaller cylinder of radius A. And it turns out, it is given by the problem that the larger cylinder, the smaller cylinder is rolling inside the larger cylinder. So we have a radius A. So this is my radius A of the smaller cylinder here, and of course the radius B of the larger cylinder is the following, and of course it is given that B is greater than A, and let us say that the center of mass of the cylinder inside is G. We are assuming homogeneous cylinder, so the center of mass will be at the center or the central axis of the cylinder. So then now we see that the key to write down the Lagrange equation is we need to pinpoint what are my generalized coordinates, right? The number of generalized coordinates will give us or will tell us how many Lagrange equations of motion we have to write. So the first equation that we have, the first variable, the first generalized coordinate that we have is theta, which is the angle that the center of mass of the smaller cylinder subtends as it rolls in the inside of the larger cylinder. And of course the second generalized coordinate will be the angle phi that the inside cylinder makes or rolls when it rolls on the surface of the larger cylinder. So we have two generalized coordinates. So Q is given by, we have theta and phi. So we can expect that there will be two Lagrange equations of motion, right? So now the other issue that we have to worry about is there any constraint of the problem, or is there any kinematic constraint or geometric constraint in the problem? It turns out that the lower or the smaller cylinder is rolling inside the larger cylinder, and it is already given that it is rolling. The smaller cylinder is rolling. So the moment it is rolling, there is no friction, there is no sliding, there is no frictional sliding, which means that we can immediately write down the fact that for the smaller cylinder, the particle at contact of the smaller cylinder with the surface of the larger cylinder will have zero velocity. Now so let us say the particle at contact is P. So at P, we see that the net velocity is given by B minus A times theta dot minus A times phi dot. So that is the net velocity of the contact point P, and this has to be equal to 0 because the cylinder is rolling, not sliding. So now we see that this is a simple kinematic constraint, and in fact this is an integrable kinematic constraint, or we are dealing with a holonomic equation. And what we do is we are going to integrate this out. So this is theta and this is A times phi. Okay. So we integrate with our initial conditions. We see that we can assume that at t equal to 0, theta equal to phi is equal to 0. At t equal to 0, theta equal to phi equal to 0. And what we get is that B minus A times theta is A times phi, right? So that is what we have with the zero initial condition. So then let us now write down the kinetic energy of the system. So the kinetic energy of the system T of theta comma phi this time will be, for the smaller cylinder will be half m B minus A times theta dot square, right? So that is the rotational kinetic energy. That is the translational kinetic energy of the center of mass. So that is my V translation. So V translation is given by this quantity I have listed. And then the second one is half I omega square, which is the rotational kinetic energy of the cylinder. And for the cylinder I is going to be half m a square. So that is the moment of inertia of the cylinder. And we see that what is omega? Omega will be nothing but phi dot, the angular velocity of the cylinder, which is phi dot, and phi dot can be found, let us call this kinematic constraint as 1. So this is going to be B minus A times theta dot divided by A. So this is from 1, from our kinematic constraint 1. Okay, so we plug this all of this here, and now we have kinetic energy purely as a function of theta dot and phi dot. And now we can further we also have to worry about the potential energy of the cylinder. So the potential energy all depends. So let us say that the center of the larger cylinder is at potential energy base 0, right? So the center of the larger, or the center of mass of the larger cylinder is at base 0. Then the potential energy of the smaller cylinder will be negative, will be reduced by a distance which is given by B minus A times cos theta. So this particular distance that I'm drawing here, so this is going to be B minus A times cos theta. So my potential energy V theta comma phi will be minus mg of B minus A times cos theta. So that is what we are showing here. Okay, so now we worry about the Lagrange. So we already have the potential energy, kinetic energy. This is again a conservative system. We have to write down the Lagrange equation of motion for theta and phi. We can do that. Let us write down the equation of motion for theta, and we don't even worry about the equation of motion for phi, because phi has been eliminated from our system using the kinematic constraint. So we will have only one generalized coordinate, which is theta. So we have just one Lagrange equation, and we see that the Lagrange equation comes out to be d dt of 3 by 2 m B minus A square theta dot. This is going to be minus mg sine theta B minus A. Okay, so when we plug everything here, we see that our equation of motion is reduced to the following. So theta double dot plus 2g by 3 times B minus A sine theta, this is equal to 0. And we see that for small oscillation, I can replace sine theta by theta, right? So small oscillation means that the angular displacement theta is small. So small oscillation. We can rewrite this equation of motion by 2g by 3b minus a times theta, and this is the equation for small oscillation. We can see that this quantity which I have circled is my angular velocity of small oscillation. So let me say omega OSC square, and my period of small oscillation t is given by 2 pi by omega OSC, which is given by 2 pi by square root 3 b minus a by 2g. Okay, so that is what we have. Okay, so then let us now look at another example. So let S be the system shown. So I am going to draw the diagram and then I will write the statement. So let S be the system shown. Again, what is the system? Again, the system is something which we have seen in the last module. We have a set of two particles. Let's say the first particle P1 is of mass M1 and it is moving horizontally along a horizontal rail, and to M1 we connect another particle of mass M2 which is theta, and this is M2 which is P2. And now what I will do is I will put in a driving force F of t on the second mass, right? So let me write down the statement now. The rail, this is a rail on which the first mass is rolling. So the rail is smooth, and the prescribed force F of t acts on P2. The rail is smooth and the prescribed force F of t acts on P2. Gravity is absent. And we need to find the Lagrange equation of motion. The Lagrange equation of motion. Okay, so that is what we have. Okay, so now again our geometric intuition tells us that there are two generalized coordinates: the horizontal motion, the horizontal variable x, that is the displacement of the first particle, and the angular displacement of the second particle theta. So then S again, so this time S is a standard system with generalized coordinate q given by theta and x, or let me call this as q given by x and theta, right? And we can start to write down. So notice that this is a problem where we have an external force in the form of Ft, which is acting on the second mass. So which means that the system is not isolated, or the system is not conservative in general. This is not a conservative system because we are driving the system with an external force. So this falls under the category of the standard system, and we have to write down the Lagrange equation for the standard system. So for the standard system we need to find the generalized forces Qj. So we see that there are two generalized coordinates of motion x and theta. So let us write down Qj of x. So Qj of x. Well, it's not Qj of x, but it is Q of x. Why? Because we are going to write down the generalized forces for both the particles. So J is from 1 and 2. 1 means first particle, 2 means second particle. So Qj is F1 of S times R1 of x plus F2 of S times R2 of x. So what is this F1 of S and F2 of S? F1 of S is the external force acting on particle 1, and similarly F2 of S is the external force acting on particle 2, and R1 and R2 are the position vectors of particle 1 and 2 at any given point of time, right? So similarly we can write that Q theta will be again F1 of S dot with R1 theta. R1 theta means the theta component of R1, and plus F2 of S dot with R2 of theta, right? And then we can write, let us say F1 of S is 0 and F2 of S, there is no external force acting on the first particle as the diagram shows, and F2 of S is F of t, and let us say our coordinate is such that the horizontal axis is the x direction and the vertical is the y direction. So this is F of t times I hat, right? So those are my forces, and my position vectors are R1 R1 is x of I, and my R2 is x plus a sine theta of I minus a cos theta of j. We can quickly write down the coordinates of the second point, the m2 is x plus a sine theta, and let us say that the zero of the system is at the point where the zero base is at the point where the mass m is rolling. So this one is nothing but the distance between the two masses is a, the fixed distance, so the vertical distance is a sine theta. So that is why we have this a sine theta here, right? And well, not a sine theta, a cos theta, sorry, a cos theta, which is here. Okay, so that is my vertical distance. Okay, so then I think we are ready now. We have given the generalized forces, the form of generalized forces. We can plug in all these formulas. Well, before that, let us also write the kinetic energy and the potential energy. So the kinetic energy of the system is P is going to be, for the first mass which is rolling horizontally, is mx square, and for the second mass which is now driven will be m times a cos theta. Why a cos theta? Because a cos theta is the vertical distance, right? So m times a cos theta, and we have that times x dot theta dot, and plus half m theta dot square, right? So m a cos theta x dot theta dot plus half m theta dot square. Okay, and we see that now the potential energy, well, what have we got here? We don't have a potential energy. Well, this is my total energy here, the kinetic energy only. This is my kinetic energy, and now my Lagrange equation of motion will be ddt of partial t partial qj dot minus partial t partial qj, and this is equal to q of j, the generalized forces, right? So then how many equations we have? We see that the Lagrange equation of motion for x dot, so we will have two equations here. So qj being, it's a vector, so for x we have the Lagrange equation as follows. So this is ddt of 2m x dot plus ma cos theta times theta dot. This is equal to f of t, and the second equation of motion is ddt of m a cos theta times x dot plus m theta dot, and then of course dt dqj, which means we have to differentiate with respect to theta. So this is my theta coordinate Lagrange equation. So theta coordinate, this is going to bring us minus ma sine theta and x dot theta dot. So that is my this derivative here. Okay, and then on the right hand side we see q2 will be a cos theta times f of t. Well, we plug how did we get the right hand side? We plug in all the formulas that we wrote down in the previous slide for q1 and q2, and now we have two equations, and these are my Lagrange equation of motion. So this is for a standard system which is non-conservative.